So in this course, we'll have two different kinds of lectures. One is the primary course lectures, and the second are the TA lectures, which should cover both the basic background material as well as the programming. So the TA lectures will help you in implementing or in understanding the implementation of all the algorithms, of almost all the algorithms that we are going to cover in this course. So the way to follow this course is to follow the primary course lectures, and to clear your doubts regarding the basic theory or the background theory or the programming, you have to follow the TA lectures. And then there would be assignments and mini projects which should be graded. And you may be ranked according to the other people who are taking this course. So now let's discuss the notations that we are going to use in this course. So here I'll just introduce you some notations, and then most of the notations would be introduced in the lectures themselves. So in supervised machine learning, we'll assume that we have a data set, which we'll denote by D, which is a set of m data points, xi and yi, where each of the xi's would be some k-dimensional or some n-dimensional real vector, where xi is some n-dimensional real vector. This n is a variable, it can be anything. And then we have some labels. These labels or the target values can be scalar, or they can be real scalar, or they can be integers. Or yi, where z is a set of integers. So we'll denote this xi as an ith example in our data set. And this xi will have n components. So the notation xij would mean that we are referring to the jth component of the ith data point or the ith feature xi. In some cases, where we will make it clear, we'll use x subscript I to denote the ith data point. But whenever we use this, we'll make it explicitly clear in the lecture itself to avoid any confusion. We will denote the probability density function of a random variable. Let's suppose there's a random variable x. Its probability density would be denoted as p of x. We'll denote the dot product between two vectors x and y. Let's suppose there are two vectors a and b. We'll denote the dot product using this notation, or we may denote it by simply as A transpose times B, where both A and B are some k-dimensional real vectors, or any vector. Which means that each of their dimension, each of the k dimensions of a vector are real value, or each of the components of these vectors are real value. Furthermore, sometimes we will say that a data set is drawn from some distribution P, which is a probability distribution. What does it mean for a dataset to be drawn from some distribution? Let's suppose our dataset contains points xi's and yi's. We'll go more into details into this when we cover the lectures where this is used. Here's a very crude discussion about what does it mean, roughly speaking, what does it mean for a dataset to be drawn from some distribution. Let's suppose we have a set of points xi's and yi's, where, as we discussed in supervised machine learning, there's a functional mapping f that you want to learn that takes in the input data points xi and generates the corresponding labels yi's. So now the goal is to find this functional mapping, right? And we assume that almost all these labels are generated by this functional mapping, which you can learn using some learning algorithm. But also there's some small noise in the data, which means that these yi's are related by this functional mapping through this equation f of xi plus some small error epsilon I, where this epsilon I is some random variable. So when we say that the dataset is drawn from this distribution, we mean that these epsilon I have some, where these are random variables, they have a distribution P. And almost for all the points in this dataset, for example, for the j data point, we'll have yj equal to f of xj plus epsilon j, where again epsilon j is also drawn from the same distribution P. It means that the errors which are independent of each other, what does it mean for epsilon I to be independent of epsilon j is that the probability of epsilon j is independent of the observation of epsilon I on the data point xi and yi. That is, the probability of epsilon j given the error epsilon I is simply equal to the probability of epsilon j. So this is what we mean, crudely speaking, that a dataset is drawn from some distribution. It means that the errors in the dataset have some distribution, and those all those errors on each of the data points are drawn from the same probability distribution P. So that's all we wanted to cover in the notations part of the course, and more notations would be introduced in the primary lectures or in the TA lectures whenever we feel that it's necessary to introduce them.